Okay, now let's do a simple exercise, which is to do a microscopic simulation of traffic. So it's microscopic, so I'll say that for all vehicles, I know the position, the speeds, and everything, but there's a constraint that the kind of simulation that I do need to adhere to replicating the fundamental diagrams because those are observed. I can take in virtually any scenario. Let's take the most simple of them, just a one lane road, and there are a number of vehicles around. And let's say I'm simulating all of them one by one. Let's write down the equation for this one. Now, if I really have to simulate this vehicle up, normally what you do, you try to increase your speed so that you travel with the maximum speed possible. So let's say that I have an inherent desire that I should be traveling with the maximum speed possible, or my acceleration should be equal to a constant times the, let's make a P controller. So my acceleration is proportional to my desired speed minus my current speed. And let's normalize this quantity up so that this proportionality becomes easy. So V max, and this of course can be written as 1 minus V by V max. And let's say that I also have a rate of change. So let's say that I change it by a magnitude of alpha. So that's another constant in terms of the power that I have included. So this is what I call as the preference to have a speed Vmax. So I need to accelerate, I should be able to go with Vmax, but of course I'll not be able to do that, because if I do that I will probably collide by this vehicle. So let's say let the space gap between them be S, and I also have a preference to decrease or decelerate. So it's decelerate, so let's say minus, so decelerate, so acceleration is negative. And I say that it's inversely proportional to what's gap that I have. So even if the gap tends to 0, I'll apply the brake using the maximum force that I can. And I'll apply the brake, and let's say it is S star. So this is the preferred gap, or here I just mention it as preference to brake so as to stop before a preferred distance. And let's say it's of course A times, so A, let me keep it as a common proportionality constant. In any case, I have got this alpha over here, so I say this is S inversely proportional to distance and another constant, and let's say it follows a square law, so it's inverse square law. So as S tends to 0, that means I'm about to collide, my retardation will tend to infinity, I'll brake by the maximum amount that I can. As S tends to infinity, so I won't retard. Why will I retard? I'll just have acceleration. I'll go by the preferred speed. Why will I show a retardation? Absolutely doesn't make any sense. I've got infinite distance. I don't care about the vehicle in front. It's after an infinite distance. So now let's say what is S star. And remember, I can, in the simulation, I will always go straight on the road, so there won't be a linear velocity and angular velocity, there will be only a linear velocity. I won't turn anything, angular velocity is always 0, I keep on going straight. So S star is the preferred distance to keep. So basically looking at a specific scenario, looking at a setting, I say, what should be my distance? What should actually be my distance? So let's calculate S star, the same road and the same scenario. And this time, let's say this one is moving with V, let's say this one is moving at V1. Using all these factors, I'll say what is the space gap that I should keep, what's the preferred distance that I should keep. Now, first of all, there has to be a constant S0, so I should keep a constant distance from the vehicle no matter what. No matter what, I should always keep a constant distance from the vehicle in front. And that's obviously known in general from our understanding of traffic. So it said that keep a meter, probably 4 meter distance from the vehicle in front, no matter what happens. I mean, a lot of uncertainties may happen, so no matter what, keep a fixed distance from the vehicle in front. That's known to us. So I say there's a constant S0, that's the distance from the front vehicle that I must always keep. Now, along with that, there's a reason to believe that if you are operating at a higher speed, then you will be more conscious of the vehicle in front, and if you're operating at a lower speed, then you will be less conscious of the vehicle in front. That's exactly what the fundamental diagrams told us, that I cannot immediately keep a large speed because my space gap is small. So if the space gap is large, then I can have larger speed. If the gap is small, then I'll have to operate at a smaller speed. That's why density behaved inverse of my speed. Larger density, smaller speeds. So let's have that effect. So if my speed is large, then my preferred distance will be large. So that's V, and let's normalize it by V max, and let's have a proportionality constant S1. Now it really turns out that you can drive at 100 km per hour, you can drive at 120 km per hour, but then when your speed increases, you don't linearly increase the distance from the vehicle in front. So that'll be too much. So let's keep a square root. So again, it's any general power, and then we try to see which of the simulations most closely predict or most closely replicate the kind of physical observations do I have with the physical sensors. So I have recorded a ground truth, and I say that which are the sensors which kind of give me the best ground truth which is possible, a replication of the ground truth. They were fundamental diagrams we made by observing real life data, so I'll regress it for all the powers. Currently, let me just take it intuitively that square root appears to be doing okay, that even when the speeds increase from 20 km per hour to 120 km per hour, the distance that I keep does not increase 6 times, so I kept a square root for it, indirectly saying that larger speed, the larger be the distance, and that makes all intuitive sense. Now, there's another factor, and that's why we say that don't drink and drive, because when you drink and drive, what happens is that your time to react is a few milliseconds. So you observe obstacle in front, and from the time that you observe the distant obstacle in front, so the time when it takes for your eyes to see, your brains to process, and your legs to press the brake, that's called as a reaction time. For the humans, it can go up to microseconds. For the self-driving cars, it's in milliseconds. So self-driving cars are not that efficient. But then what's the problem? The human drivers, when they are drunk or they are fatigued, it becomes from a few microseconds to a few milliseconds, which is still not very good. It's okay. When you are extremely fatigued, it's still 100, 200, 300, 500 milliseconds depending upon the fatigue. But then when you are heavily drunk, your time of reaction could be up to 2 seconds. Now imagine you driving at 100 km per hour. For 2 seconds, it's taking from the time your eyes see to your legs reacting. So 100 km into 2 seconds, or 2 by 3600 millisecond hours. So for that duration, your car is just moving. So your car virtually moves a few meters without any control. That's called as a reaction time. So I need to say that, okay, this preferred distance is okay, but for me, in order to do any kind of a reaction, for me to react to anything, I require t reaction amount of time, and within that time, the vehicle will move by a factor of T react, this is my reaction time, times my current speed. So from whatever distance I maintain, this needs to be accounted in addition, or I'm moving this thing and suddenly something happens. So for T react times V, I do nothing, I just move. After that is when I'll start braking, and once I start braking, imagine if this suddenly stopped. Imagine if this suddenly stopped, I'm braking at V. So what's the least distance that I travel? That's of course V square is equal to U square minus 2AS. So U square is my current speed, which is V. So it's V square divided by 2A. So this is distance to keep if vehicle in front suddenly stops. And in other cases, you note this thing as the relative speed. So if it suddenly stops, and this is the distance that you must keep, and in general you say that I'm traveling at V, this person is traveling at V1, so the relative speed is V minus V1. And because the relative speed is V minus V1, does it make sense to keep V minus V1 the whole square divided by 2A distance from the vehicle in front, so that I can stop, I mean assuming that V1 is smaller than V, so that I can stop in good time without causing a collision. So let's do a mixture of both. So I say a mixture of both these, so it's V times delta V divided by 2, and instead of acceleration A, I take it as a geometric mean of acceleration constant and a deceleration constant. So that's another distance that I need to keep. Or T react times V is something that I travel without knowing anything. Then, in order for me to immediately stop, I require approximately this much of a distance. After this, I'll stop. After this, I want an additional S0 distance, so that I don't, I mean, even if I stop suddenly, it's not that once I stop suddenly, then my back bonnet is kissing the front bonnet of the vehicle in front. There are uncertainties that we haven't accounted for, uncertainties in kinematics and parameters and knowing the position. In any case, the humans don't brake so as to just kiss the vehicle in front. They keep sufficient distance, so that's S0. So in short, I've got 4 factors which give me what is my preferred distance from the vehicle in front. The first one which says that if I have a reaction time, and that reaction time is taken, so for T react times V, I do nothing. The second factor that I say that, okay, if the vehicle in front suddenly stops, then what's the distance that I require, and if it doesn't suddenly stop, it's going at V1, I'm going at V, so delta V is V minus V1. So how much distance should I keep taking into factor? So geometric mean of both the factors, delta V divided by 2 root AB, where A is the acceleration constant and B is this retardation constant, because delta V could be positive and there might be a need to keep in smaller distances as well. So it's an acceleration and a braking constant, a geometric mean of that has been taken aside. And then of course there's general rule. So a general rule that just says that larger be the speed, just keep enough of a distance. So these are different factors using which I've calculated what should be the distance that I should be keeping in from the vehicle in front. So how the simulation really goes along is that now I just need a linear speed, and therefore I need just one control law, which is this one, and this is the equation that I use to get my preferred distance, which goes over here. So there's just a linear speed to operate, there is just a linear speed that I need to control. So that's how I'll manage my acceleration and a brake, that's how I'll simulate the vehicle. And the good thing is that there are a lot of primitives from the fundamental diagrams that we have already incorporated into this as an equation. So we've already accounted for the fact that the larger be the distance, the more will be the speed and vice versa. We've also said that without a vehicle in front, I'll accelerate and I'll reach Vmax. So if there's a vehicle in front, the nearer it is, the lower I reduce my speed. So these fundamentals are already accounted for, and because these fundamentals are already accounted for, it gives me a nice reason to believe that if I simulate this entire system and I plot the same fundamental diagrams, which will be interesting because I'll do a microscopic simulation and my fundamental diagrams, they tell a macroscopic story. So if I still draw the fundamental diagrams, I'll get in exactly the same figure. Now there are many constants around over here, so what I'll of course do is I'll collect a lot of ground truth data using intelligent vehicles, using loop detectors, using smart cameras, using the traffic data which is available with the transportation authorities, and I'll see with a simulation how closely do I replicate the actual ground truth which is available, and if I am able to pretty closely replicate the ground truth, that will be a good simulation. That's why you see so many constants, and the constants are something that could be regressed based on whatever ground truth data that you have, based on whatever data that you have collected from the realistic on-road settings, and that's how I will set in what those parameters are.